Okay, so we left off last time starting to talk about maximum power transfer, or maybe we should say maximum average or maximum real power transfer. And we're going to start to discuss this just like we did last term in the DC case with a Thevenin model. So if I take this Thevenin model, what's to the left of this dotted line, and add a load to it, the question comes up, what value of impedance Z sub L for this load right here do I want to put in there so that I can maximize my power transfer? Because if the value of the impedance is too low, voltage or current might be too low. If it's too high, then the other one will be too low. So I want to get it just right so I can maximize that power transfer. So some of our conclusions you'll recognize, but some of them will bring up new topics. So if I start out, I could say that the voltage across this impedance, this load impedance, Z sub L, would be V sub L, and the current then through the whole thing, this is just one loop, would be I sub L. So I could talk about the average power for that load as being equal to 1/2 V sub L, so I'm using maximum values here, peak values, I'm not using RMS values, so V sub L times I sub L times the cosine of the angle of the voltage, that being theta, minus the angle of the current, that being phi. So that's the expression we've seen for quite some time as far as average power goes. So now I need to start making some substitutions. I can talk about the Phasor form. So this is the phasor for the current, I sub L, and that would really be equal to just the voltage divided by the total impedance, right? So I could say that if I took this voltage V open circuit or V Thevenin, whatever you want to call it, I'll call it V open circuit, and I divide by Z Thevenin plus ZL. So I add those two impedances together, that becomes the denominator. Take the voltage, divide by the total impedance. That gives me the current, hopefully pretty straightforward. And then if I want to find specifically VL, really as a function of V open circuit, I could use voltage division, right? Voltage division will give me, what am I going to have? V open circuit, I start with the total voltage. So V open circuit is a phasor, and then I multiply by that Z sub L, because that's the impedance that I'm looking for to cross, and divide by the two impedances, Z Thevenin plus ZL. Okay. So what I'd like to do is break those into magnitude and angle form. So if I look then at the magnitudes, so let me talk about the magnitudes of I sub L. So I won't put a phasor on there. I'm talking about the magnitude. What's that going to be? Well, it'd be the magnitude of V open circuit. V open circuit. And then how do I find the magnitude for Z Thevenin plus ZL? Well, it would really be R Thevenin plus RL, quantity squared, plus X Thevenin plus XL, quantity squared. And then I take this whole thing and I take the square root of it. Okay, a little bit like adding vectors. Now, if you imagine that you have this triangle here where you have R Thevenin, and then you have X Thevenin, and you want to add it to this one over here that you have RL and XL, and it looks like both of those are inductive. I mean, you could think of one as one and one of the other, but that's what you'd have. You're just going to add those using the Pythagorean theorem. So that would be the magnitude of that. And likewise, then, if I want the magnitude of VL, I could say that that was the magnitude V open circuit. And then this is a little more complicated. I have to deal with that Z sub L, which would be RL squared plus XL squared. Take that to the 1/2 power. And then nicely, the denominator would be exactly the same thing as the current. Okay, and that's going to be handy before we get done. So that's the magnitude. So And the reason for this is I need the magnitude of this one, I need the magnitude of that one, and now I have to deal with the angles. So let's say that I come down here and look at this RL and XL. There's an angle in here. That's going to be the impedance angle, isn't it? Okay. So if I talk about the angle, I could say that the angle of the voltage, so that's the voltage, minus the angle of the current, theta minus phi, this is the current, that's really equal to theta sub z, the impedance. And if this is for the load, then I'd say theta sub z for the load, right? Okay, so if I look at this triangle, maybe I'll make this triangle a little bit larger. There's RL, and it wouldn't necessarily need to be inductive, but let's say that it looks like it's inductive, just so I don't have to draw two triangles. There's my theta sub z for the load. This is a right angle. So let's talk about the cosine of theta sub z for the load. By definition of cosine, you learned way back in trigonometry that that was the ratio of what? The adjacent over the hypotenuse, is that right? So what's adjacent to this angle? R sub L. What's the hypotenuse? Does this have a hypotenuse? Yeah, square root of RL squared plus XL squared, taken to the 1/2. Okay, so that's the hypotenuse. RL squared plus XL squared taken to the 1/2. Okay, so now I've got this piece here. I've got the angle. So when I substitute those in, into 1/2 VL IL times the cosine of theta minus phi. No one wants to do the real substitution, but let's look at this thing. I'm going to have these two, right? They have the same denominator, and it's a square root, so when I multiply them together, I get the denominator. That'd be kind of nice. And then this numerator here, this RL squared plus XL squared to the 1/2, that's going to cancel with the denominator there, isn't it? So I'm going to have something that looks like this, that the power in the load is going to be equal to 1/2 times, I'm going to have that V open circuit and this V open circuit running around, so I'll have V open circuit squared. Now we've got this RL from there running around. RL. This canceled with that, and then I'm left with R Thevenin plus RL squared plus X Thevenin plus XL squared. Okay, so when you make the substitution and you go through the algebra, that's what you come up with. So, now, I'd like to maximize this, right? Yes? Uh-huh.
In all our work is magnitude, what is the X that
X sub L? Well, this is X sub L, which is probably not a very good subscript because we confuse that with inductance, but that's the load. And that would be either omega L or 1 over or minus 1 over omega C. So it's the reactive portion. That's the imaginary portion. Okay. Are there questions there? So if I build on this here, we would like to, we want to maximize P load. Okay? So by doing that, I can minimize the denominator. Okay, and one real good way to minimize the denominator is x Thevenin, whatever the reactance of the Thevenin is. If I set it equal to minus XL, then that term goes to 0, right? You might say, well, that's going to cost you power, but the reactance doesn't dissipate any power. Okay, the reactance, the imaginary term, does not dissipate any real or average power. So there's no downside to setting my load impedance, putting a negative in front of it, setting it equal to the Thevenin impedance. Okay. So with that, then this term goes to 0, right? So I get to rewrite this, that power for the load is equal to 1/2 times V open circuit squared times RL divided by RL plus R Thevenin squared. And with the exception of the 1/2 here, because of the V open circuit being in a magnitude form and not an RMS form, we have over here exactly the same thing that we had with the DC source. And how did we maximize that? From our DC work, the maximum was when what? RL was equal to R Thevenin. We went through the, you can go back to the lecture from last term, but we went through the calculus, and we found that that was how we got a maximum. So now, we can say for maximum power transfer, we want the RL to be equal to R Thevenin, and we would like what? The XL to be equal to what? Oops, not equal to, too many there. Minus JX of Thevenin, right? Okay. And there's a mathematical term for this. It is called the complex conjugate. So we could say this thing is Z sub L, that's the impedance of the load, would be equal to the conjugate of the Thevenin impedance. Okay, of the Thevenin. So this is the conjugate. Okay, and the conjugate is not particularly complicated. If you want to take and say that you have A plus JB, if I take the conjugate is A minus JB. What if you have this in magnitude angle form? Magnitude at some angle, let's not use theta and compute, just some angle alpha, if you will. If I want to take the conjugate, that's going to be magnitude at minus alpha. So invert the sign, change the sign, flip the sign, however you want to think about that, either on the imaginary portion or on the angle when it's in a polar expression. So our conclusion here is that we get maximum power transfer when the load impedance is equal to the complex conjugate of the Thevenin impedance. Which doesn't negate what we did last term. RL still equal to R Thevenin, isn't it? It's only the complex term that we have to be careful of. Questions with that? Well, we've got some problems where we'll get to use that. We'll spend some time on next time in lecture, spending a lot of time working on problems because we've got a whole bunch of problems that can take quite a while to come up with a Thevenin model, as you remember from last term. So we get a lot of practice with that. But before we go into that, I would like to finish up our discussion on power and talk about the rest of the story, as Paul Harvey would say. We've only talked about average power, it seems like, and we've ignored part of the power triangle. I don't know that we've even used that term. But what's going on with those x terms, with that j omega L or minus 1 over j omega c, minus j over omega c? And the rest of the story is complex power. So I'm going to define complex power with the symbol S. That's the symbol your author uses. That's a complex number. And we'll say complex power is S, which is equal to VRMS times IRMS conjugate. Okay? So again, this is the conjugate term. And you'll see very shortly why you would want that term to be a conjugate. What's that? The little star? Okay. So if I look at this in magnitude angle form, I could say that VRMS is really the magnitude VRMS at some angle theta. We usually use theta for voltage. And then IRMS is the magnitude, and if I take a conjugate, I get the negative sign. That's due to the conjugate. Okay. So if I go through my math there, I multiply the magnitudes. That's apparent power, isn't it? If you want another name for it. And then I add the angles. Well, what's theta plus a minus phi? Theta minus phi. Does this ring a bell here? What's theta minus phi? That's the difference between the angle of the voltage and the angle of the current. Do we know what that is? That's the impedance angle, isn't it? Theta sub z. Okay. Well, we could express, if we wanted to, this complex power, S, in a magnitude and angle form. And sometimes that's useful, but I think I would like to express it in a rectangular form here, where I can say that the complex power S is equal to the real portion, which is the real power, or sometimes we call that the what? The average power. So the real portion of complex power is average power. And the way that, this is probably starting to spin in your mind here. It's like, oh, make this stop. Well, the real way to figure this out is by the units. Okay? So real power or average power, that's in watts. We've been using that for a long time. Then the imaginary portion of this is what we call reactive power. It's the reactance, reactive power. That hopefully makes sense. I don't think I spelled that right. T-I. No, I guess R-E-E-A. Yeah, I'm missing a C in there. There we go. Okay, reactive power. And sometimes I think it's kind of old school, but sometimes they'll call it quadrature. Okay, so if you see it reading a book and they talk about quadrature, that's reactive power. Okay, and the units on it are volt amps reactive. And people never like to write units anyway. They certainly don't like to write long things like volts amps reactive. So it's VARs. So if someone's talking about VARs, what are they talking about? They are talking about reactive power, the imaginary portion of complex power. Well, what's the units on complex power? Well, the units on complex power are volt amps. Well, no one likes to write out volt amps, so we use VA. So if we were to look at this as a triangle, where I put the real portion on the horizontal, and I put the reactive portion on the vertical, and Q can be, this would be a positive Q. You can have negative Q. There's positive Q. There's minus Q. Okay? So you can have something like that. Okay. But here, on the real portion is the watts. Here in the imaginary portion, whether it's positive or negative, is the VARs. And then this hypotenuse, that's the complex number, the combination of that, the complex power, that's volt amps. So the units are a real help in sorting out what you have. Well, this triangle is important because this angle here is, again, the same angle as the impedance. So the impedance triangle and the power triangle are similar triangles, and I don't mean that to say that they're very much the same. I mean that to say that they are mathematically similar. They share that same angle, so they're mathematically similar triangles. Let me look at this at a slightly different twist. So let's say that we have a circuit here, piece of a circuit rather, and it has a resistor, which the real portion of the impedance, that's just the resistance, isn't it? And we could talk about the impedance here, and I'll just put a box. What's going to be in that box is either a capacitor or an inductor. Okay? And that would be the imaginary portion of the impedance, which would be equal to minus 1 over omega c or omega L. So if I talk about the current going through this, and we know the current goes through both of those, so the current is something that we like to talk about. We tend not to like to talk about voltage, because if I talk about the voltage across the impedance, I have to divide it between the voltage across the resistor and the voltage across the imaginary portion. So if I want to talk about average power, I could say that it was I squared times the, and this is RMS, so I don't have that half term, I could say it was I squared times the real portion of Z, right? I mean, this takes us back to our good old friend, I squared times R, right? And if I wanted to talk about the reactive portion, I could say that it was equal to I squared RMS times the imaginary portion of Z. What's that? Well, it's either minus 1 over omega C or omega L. And if we wanted to then get this hypotenuse here, we could say that it was equal to I squared times the impedance Z, where I take both of those pieces into account, both the real and the imaginary. Okay. And again, what are the units here on this term going to be? This is watts. What's this going to be? Bars. And then over here, VA. Okay. And you're all probably pretty comfortable with watts. Most consumer products, you turn them over, you'll get watts. If it doesn't say watts, it will say VA. Okay. But VARs is a little different. But this is the whole story. If you wondered, well, we're only looking at part of the picture. Yeah, we were only looking at this piece with average power. There's more out here. So let's try and pull this all together in an example. This will probably be a fairly long example. I don't know that we'll finish today, but we'll get started and give you something to think about, hopefully. So we're told a load operates at 240 volts RMS. The load absorbs an average power of 8 kilowatts at a lagging power factor of 0.8. We'd like to find the load's impedance and its complex power. Okay. So again, I spent the time to write this out so that we have to sort out from the verbiage, because that's the difficult part. I mean, that's the difficult part in life is communication, right? Everyone's always calls something different, don't they? Go somewhere else, they not only say it with a twang, but they sometimes use a different word, don't they? I'd like a soda, or I'd like a pop, or soda pop, or Coke, or whatever. Everyone has different words for things. So we'd like to find the impedance. What's that? That's Z, isn't it? And we'd like to find the complex power. We know that that's actually S. Okay, well, speaking of power, I could look at a power triangle. And if this is, that's not a very clean triangle. Let's clean that up a little bit. So we know the hypotenuse, that's S. This is going to be the average power P, and this is Q. And what have they given us? They've given us that the average power is 8 kilowatts. So we know this is 8 kilowatts, isn't it? They've given us one side of that triangle. Now we might say, if they've just given us the angle. Well, I think they have. This is theta. What do we know that the power factor is? I mean, if we go back and thinking about an exam, maybe we should start writing these equations for practice, but the average power is equal to the apparent power, which is V RMS times I RMS times the power factor. Didn't we see that? And that's because the power factor was really what? Cosine of the angle of the voltage minus the angle of the current, which was really equal to what? Cosine of the impedance angle, wasn't it? So now I can say if the power factor is 0.8, I have 0.8 is equal to the cosine of theta z. So what's theta z equal to? Arc cosine of 0.8? Is that right? So I have 36.87 degrees. Take the arc cosine of 0.8 and I get theta z. Okay. So now what I have, I've turned some fairly confusing verbiage into hopefully a fairly easy geometry and trigonometry problem. 36.87 degrees. That's a right angle. And I have 8 kilowatts there. Can I get the other sides? Yeah, I mean, if I wanted the hypotenuse here, I could get that, or I mean, I could get this too, couldn't I? This is Q. What would that be equal to? Well, I could say that, maybe I'll write it here. The opposite, Q, over the adjacent, 8K. Opposite over adjacent is what? Tangent? 36.87. So Q is going to be equal to 8K times the tangent of 36.87. What's that turn out to be? 6? 6K. Now I was pretty careful. I wrote this as 8K. I didn't write it as kilowatts because this is going to have a different unit. This is going to be what? Vars, isn't it? So 6 kVars. Okay. So let's see. Do I know about S then? Yeah, I mean I could write S in rectangular form, couldn't I? I could say that S is equal to 8 plus J6. And this would be kilowatt. Volt amps. So that'd be my answer for S. That's as good as any answer. You can put it into a magnitude angle, but that's fine for now. So the one thing that I take away from, we're not done with this problem, but from this portion of it is draw your triangles. Turn this kind of ugly electrical terminology into very simple geometry and trigonometry. Well, we were asked for the impedance. So let's see if we can get that. I'm going to take a bit of a side here. So we'll say on the side. Your author comes up with an expression and says, all of a sudden says that the complex power S is equal to V RMS squared, the magnitude squared, divided by the conjugate of the impedance. Which would really be handy in our case, wouldn't it? Because we know the voltage and we just found S, we could get the impedance in one fell swoop, wouldn't we? But the question always comes up, I mean, where'd that come from? Does it work and whatnot? So let's see if we can prove it. So I could, so say our proof, put this in quotes. So didn't we say that S was equal to, by definition, V RMS times I RMS conjugate. Isn't that how I started out with complex power? Okay. So I'm going to write VRMS a little bit differently. I'm going to say that that's magnitude RMS, whatever the magnitude is, and I'm going to say that it's the angle theta. That's the angle we usually give to voltage. And I will multiply that then the current. I'm going to say that that is VRMS at some angle theta divided by the impedance Z. Because if I take voltage and I divide by impedance by Ohm's law, that gives me the current, right? Okay. So no sleight of hand here yet. So let me work on this a little bit. I could say that this was V RMS at theta. And then over here, again, V RMS at theta. And I'm going to divide by, let's see, Z. I'm going to take the magnitude of Z. And what's the angle of the impedance? It would be the angle of the voltage, theta, minus the angle of the current, phi, wouldn't it? Okay. So I'm going to do the division there. I'm going to say that I have V RMS at theta. And then inside the square brackets there, I'll say that I have V RMS divided by the impedance Z. And what angle is that going to be? If I take theta and I subtract theta minus phi, I come up with what? Let's see. Theta minus phi would be theta minus theta plus phi. Wouldn't I get phi? I would get phi. Okay. So then I'm going to take the VRMS out and square it. VRMS, so that magnitude will be squared. And then I'm left with 1 over Z. And then I have an angle. Let's see, when I multiply, I'm going to add, so theta plus phi, right? Do I want to do that? Let's see. Yeah, I don't think I want to do that yet. Do I want to get there? Oh, yeah, I've messed this up from the get-go, haven't I? Okay, so I haven't put the conjugate here. So let me put the conjugate here, which means that I would have a conjugate there, which means that I would have a conjugate here. And if I want to get rid of that conjugate, I could just put a negative on that, right? So I'd have theta minus phi. So I'm going to get rid of the conjugate, and I'm going to put a negative right there. So I'll say that that from the conjugate, that's where that negative comes from. Okay? Okay, so I think I'm back in business now. This should be better. So V RMS squared times Z, and I have Z in the denominator. And what if I wanted to put that angle with Z? How would I get that angle in the denominator? I mean, what we have here, where we have theta minus phi, that really is equal to the impedance angle, isn't it? I mean, that'd be the angle of the voltage minus the angle of the current. So what if I put this as minus theta sub z? Will that work? Yeah, putting in the denominator, I put a negative sign on it. Well, I don't like that negative sign in the denominator, so I think I'm going to write this, that I have V RMS squared times 1 divided by, I could just say that this was Z conjugate, couldn't I? That's the same thing as saying take the angle of the impedance and put a negative sign in front of it, isn't it? So finally, I could say then that the complex power S is equal to V RMS squared divided by the complex conjugate of the impedance. Okay? So that's what we started with, and that's how you get there. So does that work in our particular problem? Our previous problem, we had that S, we found, was equal to 8 plus J6, and that was kilovolt amps. And did we have, what was our VRMS? That was given in the problem, right? I mean, there's our S, where's our voltage? 240 volts RMS. So 240 volts RMS. So we can say then that the impedance Z, or I should say Z conjugate, would be equal to V RMS squared divided by S. Just rearranging that expression. So I've got 240 squared divided by what I'm going to have for S. 8,000 plus J 6,000. Remember I had K values, so I'll put those thousands in there. So that should work. When you grab your calculator and you run through that, you come up with 4.608 plus J 3.456. The whole thing's in ohms. All right, what can we say about this? No, that's not. This is. I better be careful with this. This is negative here, and this is. We were looking for the conjugate. So now one more step. What is Z? 4.608 plus, because I switched the sign on that, plus J 3.456 ohms. How did I know that I had a problem there? It's because if a lagging power factor, when you see lagging power factor, what do you think? Inductive, right? Lagging power factor is inductive. So what are we going to expect this value over here to be? Got to be positive, doesn't it, if it's inductive? Okay, so that's how I knew that I was off by one step there. So that's a pretty good way to get the impedance if you remember this equation. We'll talk next time when we get together about another way to do it, which is probably not as easy as using this equation, but is maybe more useful if we forget that equation. So we'll come back to this problem. We'll start with this problem and do it again. I'm sure I'll see some of you at the review session tomorrow. Take care till then.